First, any questions?
What are the answers to the midterm?
A, B, A, C, B, A, not necessarily in order. Try again. All right. So midterm Thursday, just a reminder. Yes.
By chance, did you walk? Oh, like all night? Did you learn when I was trying to go through and look at like the quizzes?
I fixed that this morning in response. So not all the quiz answers were viewable. So I went through and after the response in email this morning and made them all visible.
We were going to have a chapter 11 homework before the quiz.
Oh, I thought I posted that. I will post it. You can look at it. It won't be due before the test,
Okay.
but it'll be what to look at. And just do everything in chapter 11. How's that? Oh, yeah, sorry about that. Yes.
What chapters will be covered on that?
What will be covered on the test? Everything since the last test. So I believe that starts with chapter 6, compliance issues. Oh, I meant to bring my book. Oh, let's go back. Or was compliance on the last one? It might have been on the last one. I had it written down. I had my notes and they're not here. So let's see. Operations security. So we had compliance and operations security. Were they on the last test? Now I have to double check that. Okay, definitely check 8, 9, 10, and 11. Let's assume 7 too, the operations security. And it may or may not be there, but let's see when. Actually, I got a better idea. Syllabus. Sorry, my mind is gone. So, okay, yeah, so human security, we'll definitely start with that, chapters 8, 9, 10, and 11. There'll be heavier emphasis on 10 and 11 because they were longer material, and especially 10 had a lot of stuff, actually both had a lot of stuff not from the book that was in the slides. So the networking and the operating system security stuff. So I'm sorry. Okay. So other questions? Let's come back to that human element of security because I love my stories. So as you know, I was gone, or you may or may not know. Anyway, I was gone for my father-in-law's funeral. It was on Friday, so I took off Thursday after class. While we're at his house on Saturday, my sister-in-law mentioned he had 2 safes in the house. He gave her the combination to 1 safe. So the older safe, which was in the garage, he got it from Lockheed Martin when they were upgrading their safe and they were just, surplusing it. And it's not a big, it wasn't a big thing. It's like a large file, small, short file cabinet, 2 drawers. So how do we open this thing? Human element security, what would you think the combination might be? Birth year, well, birthdays, good guess. That's what I would think. That's what I tried.
It might be similar to the other factors.
Might be some of the other combinations, so that would be a good test. So they were gone. I was running some errands. I think taking a load to Goodwill. I was trying this, wouldn't work. The thing made weird clicking noises. And then I remembered something. Oh wait, this is a more, GSA, Government Services Administration approved safe. That means it's special. So this really old safe with a dial combination. You turn left, click, turn right, click, turn left. No, you turn left 4 times. You turn right 3 times. You turn left 2 times. Then you turn right once until it can't move anymore. Then you can unlock it. So you have to know that. How do you figure that out? That safe does that special thing?
Research on it.
Yeah, Google's your friend. I Googled the safe name. I saw the manufacturer, looked through a couple of, oh, there it is, operating manual. Saw the default password. I said, nah, it wouldn't be that. Default combination 50, 25, 50. No, it wasn't. But saw the 4, 3, 2, 1, boom. Then my sister-in-law came back. I said, do you have the old other combination? Because that was a good idea. She brings me the piece of paper with it, and she says, and there's this, and I see on there another set of numbers written, which was a combination of 2 different people's birthdays, which I would have gotten that one eventually because it wasn't that hard of a combination. That was the right one. We got the safe open. But it was, even if we didn't have that number, I think we would have gotten it open without having to drill it. Human factors, oh, they're just using combinations of birthdays. He shouldn't. He should have known better. It was his coin collection. It wasn't really, really valuable stuff. It was a lot of proof sets and a whole bag of wheat back pennies. He loved his coins. But human factors, people will do things. Even people who know better will do simple things. We'll pick passwords that are common. We'll share passwords again and again. I have hundreds of accounts. How many passwords do I have? So I check something because there's a set of accounts I have where I'm willing to let Google save the passwords. I don't care about these. I personally really don't care about these passwords, and they all have the same password. And I checked, and 50 of them have the same password. And then the ones I care about all have different passwords. But when you're thinking about this human element of security, what could go wrong? What are people going to do? People want their lives to be easier. They want things to be simpler. They don't want to go through the burden. They will often turn off security features or do things to make things easier. Write that password on a sticky note on the ceiling. Just think about these things, okay? When you're going through the test, think about that. The people will make mistakes. So just remember that part. What else do we cover? Where's my slides? After human element security, whoops. Physical security. Okay, the safe was kind of physical. And it was really heavy. There's no way anybody moved, especially with a bunch of coins in it. It was even worse. ATMs, they're heavy, right? They're filled with money, though paper bills instead of that, but they're made heavy. Can you steal one of those?
Oh, yeah.
Oh, yeah. How would you steal one of those?
There's a guy in my hometown with a group of people that took like a big chain and they just wrapped it around it and pulled it out with their truck.
Put a chain around it, pulled it out with their truck, probably a Ford F-150, right? Someone with real pulling belt. I've seen back people with forklifts do the same thing. Get the forklift under it, lift it up, haul it off. Then you can break the case open, and inside is another safe where the actual cash is. That is actually really hard to break open. But how do you open the main case? Well, you break it open, you go to eBay and buy one of the keys. Because there's so many keys out there available that people can get, and they're default keys for opening the main case, not again where the actual money is. But people have used that, open up the main case, put in some monitoring devices, electronic surveillance to capture people's cards and pins and stuff. So we have to think about that. When we're thinking about physical security, there's lots and lots of issues. I'm not as worried about meteors anymore. Apparently, if one can land on the bed next to a woman, she survives, I'm good. Though if it had landed on her, that would have been a different story. It was about this big. Why would it not hit really, really hard and destroy your house? It was this big and it fell from space. Trees? No trees, no. Atmosphere. Things hit the atmosphere, they're going to fall at terminal velocity. That's the maximum speed something can fall in atmosphere. And so I don't care if it fell off a 3-story, it's basically the same as if it fell off like a 3 or 4-story building. Something like that. It really can't get any faster. I was talking to my brother-in-law about this. He has a degree in astrophysics. And so he was saying, explaining why it wasn't as big of a problem. Okay, but we still have to worry about people breaking windows, people cutting power lines, people tapping into our physical security. I will do physical security. I'll have cameras and monitors up. They can be tampered with. The thing I want people to remember when it comes to physical security, and I didn't really talk about this earlier, physical security, we often tap into computerized systems and we digitize things, fingerprints, retinal scans, face scans. It all becomes this is all physical, but then it enters a computer system, it's all digital. Somebody can get into the computer system, they can copy the credentials, they can modify things, they can tweak things. So no matter how physical it is, if they're in the computer system, they could possibly bypass the security. So just something else to think about. What type of controls are there, the physical security ones? I think we talked about 3 types. Deterrence controls. 2 others.
Preventative
Prevention controls
and detection.
and detection controls. You should know about those. You should be able to give examples of them. Or I could give you an example, you can tell me which one it is. You know, the sign up, warning, attack dog. It would be what? Deterrence, yeah. The actual attack dog, not the warning song, but the dog chasing somebody would be more of prevention, possibly detection, because they can also hear and smell. It was amazing. My in-laws had their little dog in the house. And somebody would pull up with the car outside and the dog immediately start barking. You know, dog would know who's outside, somebody's outside. Not nobody else would hear it, but they're much better at that. They're very good at smelling too. So, all right. Networks, there's a lot there. Understanding the layering, physical layer, logical link layer, network layer, transport layer applications would be sufficient. The transport layer, I might ask questions about things like you have the header of the transport layer protocol, the TCP, transport control protocol. It doesn't contain the IP addresses of the machines that are talking to each other. How would the host know? How would the receiver know who to respond to? They just get the TCP message. Any thoughts on that? Does the computer that received the message know the IP address and who sent it? What?
It should.
Should, because it receives the whole packet, which has the IP header that wraps around the TCP one. If you were designing this system, you would say, hey, I'm going to give the application a way of asking me what was in that TCP header. Tell me what was the IP address of who sent me this message. And usually the libraries do that. So I could say, respond to this person at their port. You know, I'm a client, I'm asking a server. So I use my machine 129.101.100.1 and send it off using my port 3333 off to their port 80, their web port. They need to know to respond to my machine at my port. Security implications are what we have to worry about with this. Can somebody read my messages across the network? Yes. To prevent that, I'll need to encrypt the messages. Can somebody lie about who they are when responding to a message? Absolutely. Bad guys lie, cheat, and steal all the time. What can I do to prevent that? How do I deal with that? These are things we have to start thinking about. I don't expect you to have all the answers to this now. But things like the sequence numbers that I mentioned in the TCP stream. We've got, when I'm starting, I would use a SYN message, SYN for synchronize, and I give you my starting sequence number. That's a random starting number, and then it goes on from there. The bad guys can't choose that random starting number correctly. You know, so things like that we have to think about. What's a three-way handshake? Right, that's when we establish communication. I send a request with a synchronization request. You respond with your own random number, your own synchronization request, and an acknowledgement of mine. Let me know you got what number I got, and then I send my acknowledgement of yours, and now we're good to go. I want to talk to you. Yes, I agree. Let's communicate. Here's my stuff. I acknowledge that I got your response back. We're good. I keep trying to get my son to do that when I text him something. Respond that you got it. Tell me okay. Yeah, dinner's ready in 5 minutes. Don't make me come find you. Just say okay. Get that synchronization back, that communication back and forth. So that's some of the main things we worry about with networking. How do I keep bad guys out of my internal network? What techniques are there? Can you name a couple?
Firewall.
Firewall, absolutely. Where do you put the firewall?
On the network side.
On the network side?
Like the internet facing side?
Internet facing side, yeah, between my main network and the internet. What's another technology? Or architecture or something?
DMZ.
DMZ, demilitarized zone. I'm going to set up a section of my network that is more apt for people to have the outside world access with my web server, my email server, that type of thing. And then a second firewall between that and my internal, more private network. Isolate things. What's another one we can use to protect my network and security?
Honeypots?
Honeypots don't really protect. Honeypots are used to detect what things are going on. They're more for research and learning what people are doing. Anyone else? Scanning tools. So intrusion detection system, monitoring your network, monitoring what's going on. So there'd be a monitoring system where scanning would be, hey, I'm trying to see what's actually running, run Nmap, NetScan, those types of things to see what's open. What else? I'm looking for one specific that nobody's mentioned yet. Yes?
Would it be antivirus software?
Antivirus software more protects the main computers. So that'd be operating system security. Though you could have a scanner looking for viruses going across the network, so that's still a possibility.
Is it the change the default accounts?
Changing default accounts. It's not a bad one. Again, that's more operating system. So I'm thinking VPN. Right, remote login, VPN technology. It goes through, tunnels right through the firewall, but it's using encryption and authentication to allow you to physically extend your local network, yet still protected. Allow people to access your local network as if they're at home while they're on travel. So yeah, while I was at my in-laws, I VPN'd in to campus to check some emails, not often. But that's things. So that's a technology, you should be familiar with how the VPN works. And very, very simply, it's software that runs on my machine and takes all network traffic through, encrypts it and sends it an encrypted channel to a server on campus, which decrypts it and then sends it on the campus network. And that one gives me a local IP address. So when I connect to it, it says your IP address and now this campus IP address. So normally I have my home address, which is through my internet service provider, through the VPN. Then suddenly if I typed in something like, on Google, I just Google my IP address or whatever, it'll show up what IP address I'm calling from. And it'll suddenly be a campus one. And sometimes if I can't remember if I'm connected to the VPN or not, I type that to see, who does it think I am? So that's a technology. Operating system security. There's all this hardening stuff that we talked about. Checking the passwords, maintaining accounts, deleting default accounts, timeouts on things, logs, audit logs, plus just how operating systems in general protect your processes with different memory management schemes, virtualization. All of this in a 1 hour or 75-minute test, yeah. Any questions on that? So a lot possibly there. It'll be similar format to the last exam. Maybe similar length, maybe a little longer. Not sure. I haven't finished writing it. Yes. Yes.
Oh, sorry. Is this one gonna be curved?
So Question about curving. I curve at the end of the semester. I add up all your points and then figure out where's the natural cut for the A's. This one though, the multiple choice questions won't be 5 points each. They'll be like 3. Because that was just a little too painful. Yes,
Do you want us to know about the different types of malware?
I'm sorry.
Do you want us to know about the different types of malware?
Different types of malware would be good. Yes. Such as virus, worm, what else? What?
Trojan.
Trojan,
Hybrid.
a hybrid, yes. So go through that list, know what those are. There's probably going to be a few more definitions to type in this one, or short answers, less multiple choice. I'm still trying to figure that. That's where I'm struggling with the balance. I want to give you enough questions you can show me what you know without killing you. And that's always hard. Other questions? Are you ready for this?
Not yet.
Not yet, but you will be. Right, good. I like that attitude. Notice he didn't say that, but I put it in his mouth anyway. Anything else? Yes.
And we should know about specifically like Windows 10 security.
So like the controls that I showed you, the Windows 10 controls, know the basics. You know, setting password, timeouts, length, locking down defaults. But yeah, the details, no. Why don't I want you to know the details? One, there's too many. Two, you know where to find them now. And that's the important thing. To me, that's the important thing when you start working in the job. You know where to, you know the information exists and you know how to find it. I mean, to me, that's the most important thing I want you to get out of your degree. Because to be honest, what I learned back in the 80s when I was in school, most doesn't apply any. A lot of it doesn't apply anymore. The specifics of the technologies. Now, I programmed in Pascal. I don't do Pascal. I programmed in Fortran and Snowball. I don't use those languages anymore. You know, but I learned how to program and how to think logically and how to put stuff together. Now, a lot of my code is in Python, which I learned in what, 2015. Because it was suddenly something I just needed to use for that tool. And so I kept doing it. Operating system, your Windows 10 didn't exist back then. There was Windows, I think, and Windows 3, I'm trying to remember when Windows 3 came out. So, but I would use MS-DOS, and then there were some other windowing technologies you could also use before Microsoft Windows really, you know, became the default for most of those machines. So yeah, learning technology keep changing. Half of what you're learning in your degree you'll be obsolete 5 years from now, or 5 years after you graduate. You know, there are career opportunities that we don't know exist yet that will exist in 5 years. You know, there's all this data science stuff. You know, this came out in 2007. There weren't a lot of opportunities for writing apps for smartphones before that. But now they're all out there. As technology changes, new career opportunities occur. You know, the buggy whip manufacturing jobs are gone. Okay, there are still a few of those, but you know, as technology changes, things do. So learn how to learn. Okay, sorry, I digress. What else? Yes.
Will the lecture from last Thursday be up on that TV?
Is it not up there?
No.
Yes, it will be this afternoon. I apologize. That's right, because I hopped on a plane. And I forgot to upload it after that. Yes. Lecture on last Thursday will be up there because that material was relevant. Yes.
Do we need to know much about network address translation?
Some. Just the concept again, a NAT, the concept of NAT, network address translation, not, you know, the basic concepts of a lot of things. Problem is I can tell you yes, yes, yes to everything. But yeah, no, not like the whole CIS study guide now. Or hardening guide now. What else? Okay, so sounds like all the questions you got. I'm going to start covering some newer material just to get you thinking. Some of this is relevant to how I want you thinking during the test. That's why I want to cover this. I'll answer questions first. Where'd it go? So technically, this is not on the test. Okay, but some of the things to think about are there. Yes.
Never mind, I asked my question.
Okay. Well, if you think about it later, or all right. So there's a lot of things when you're developing secure software, and that's the next module that you have to think about. But these are also related to developing secure systems, secure operating systems, secure networks. And that's and some of it deals with the human element of security. And that's why I kind of want to put it all in there. Okay. Most importantly, this third element, Salter and Schroeder's paper. Okay. Let's first talk software security. Software is a collection of instructions and data that tell a computer how to work. Software bugs are errors, flaws, mistakes, or oversights in programs that result in unexpected and typically undesirable behavior. Now, I will stop right here. Some of you I know will never end up writing software. Most of you will. But those who aren't cybersecurity majors, for example, may never end up writing software. But you may interact with somebody who's writing software for you. My father was one of those people. My father was the guy who walked into the programming shop in the business and said, all I want is, and then he'd outline an idea for a tool, a system, a program that he wanted, you know. And it's those people who need to interact, who have to know something, should know something about security, should know something about secure designs. You need to be able to talk to them if you're writing the code. They need to understand something about security to know that maybe what they're asking you is unreasonable. Okay. Software vulnerabilities are specific flaws or oversights in a piece of software that allows attackers to do something malicious, like expose or alter sensitive information, disrupt or destroy a system, or take control of a computer system or program. So vulnerabilities are specific bugs that typically we believe can be exploited to cause harm. Software security is the application of techniques that assess, mitigate, and protect software systems from vulnerabilities and attacks. Cyber 220 is our course that focuses heavily on this. When you're developing software, as with when you're developing almost any other system, there's a life cycle. You start with planning, right? And by the way, those of you who are taking programming classes, you don't start with the coding, you start with the planning. Okay, you should start with the planning. My son's in CS 121 right now, and he's a math major. So that's gonna be the last programming class he ever takes. But I was trying to get this through his head this semester. He said, I'm in problems with this. Well, you know, what's your design? What's your plan? I don't know, I just started writing the code. No. Well, he knew pieces of it. And yes, how do you write what you don't know what you're writing? I don't know. But that's what authors do, right? No. You plan, you think it out. Okay. You analyze your plan, you analyze the system, you analyze what's related, and then you design. So part of the plan and the analysis is figure out, what do I want the system even to do? What are the inputs? What are the outputs? How does it interact with the rest of the system or the rest of the world? Now let's design at the high level the pieces of the puzzle. Then let's code it up, let's implement it. And often this is done cyclically. It's like maybe our planning, there's a thing they call user stories. So this piece of software, say I'm writing a word processor, right? So I need somebody to be able to type in the story they're writing, whatever they're writing in the word processor, and save it to a file. That would be like the first thing I would deal with. And then I would deal with adding images, maybe version control and edits and tracking those and all these other features. And each time we'd go through, okay, here's the new features you want to add. Here's how they're going to be added. Here's how we design it in the system, implement it. Usually when I'm at the beginning, the first thing I think about a design when I'm first building a piece of code is how can it be extensible? How can people add and modify this? Build it so it can be updated. Okay, so we get their implementation, testing and integration, testing the individual pieces of code you wrote, the combinations of code, so you get a whole program, the whole program in the whole system that it's running. Maintenance phase is while it's out there deployed, keeping it up to date. You know, if there's bugs or errors or changes in the environment, you have to update it. So like my iPad, I regularly get updates to some of the software. The apps are up there. When there's a major update to the operating system, often you see a lot of updates to the apps too, because something changed in the operating system. Where do we start thinking about security?
Right from the start.
Yeah, right from the start. Start with planning. Now, each of these, I say, provides deliverables used by the next one. Where do we do security in these 6 phases? Testing, implementation, every single phase, you should be thinking about security. Because like part of maintenance is if I'm updating it, am I breaking it? Early as possible from the planning phase, and consider security at every stage of the life cycle. Oh, good, we got the right answers. When there's a vulnerability, we have to consider where that vulnerability occurred. Now, Nancy Levison was a researcher at University of Washington for many years who looked at software safety. And then now she's at MIT. I think she's still at MIT. She may have retired. And she did some studies of software systems that failed that caused injury or damage. 50% of the problems were design problems. Somebody designed the system incorrectly. The programmers implemented the design correctly, but the design was bad. So there's one where for a safety feature at a processing plant, like a smelting plant or something in England, you know, you had to shut down A before you shut down B. The problem was device on A broke. The operator couldn't shut it down, was trying to scramble the system to shut down B. The design said you couldn't, so the code didn't let him. He didn't die, but when the explosion did hospitalize the guy, the operator. Because he couldn't shut down the system because the software didn't let him. High-level issues with program architecture, requirements, base interfaces, key algorithms, assumptions you make, you know. I got to let everybody use this system. Then there's implementation vulnerabilities. These are the ones in the design of the low-level program pieces, the actual coding, parts of individual functions or classes, you know, buffer overflows, typos in your code, other things. And they may include more complex logical elements that are not normally addressed in the design. Design's high level, it doesn't deal with the details of how it's implemented. So just think about those, because sometimes, yeah, I wrote it right. I successfully coded the wrong thing. Again, a secure computer system is one that does what I should have told it to do. Then there's operational vulnerabilities. They arise through the operational procedure and general use of the piece of software in a specific environment. Result from the application's configuration, maybe, you know, where the firewall's designed correctly, the firewall's implemented correctly, and my first rule is allow all. I configured it incorrectly. That's an operational vulnerability. I wrote you know, I use a bad password. I tell everybody my password. I give anybody who wants access to the computer system. You know, and so somewhere between the developer administrative personnel is where the responsibility. Sometimes the developer can stop you from doing it. One thing we've argued with when we've worked with people is we say, we want you to build another tool that you didn't think about building. One that scans the configuration and sees if the configuration meets these certain properties for the environment in which it's running. A lot of them will eventually agree that's actually a good idea. They've developed the system, they developed how it reads configuration data, but they never thought about checking the configuration data was other than well formatted, but it was well configured. Dr. Conte de Leon, his PhD, he looked at things where there was an example where it was a configuration file for an airport. Huge history behind this. I won't go into all the history, but one of the versions was the low altitude warning because there was a mountain. This was a island airport and there's a volcanic mountain nearby. And in bad weather, you couldn't see the mountain, you could crash into it. So there was a low altitude warning that got turned on when an aircraft approaching the island got too low. It would inform the air traffic controller. So turned on at say 50 nautical miles away, it would turn on. Hundreds of lines later in the config file was a place where they turned off the low altitude warning because basically they got tired of the low altitude warning as the plane's coming in for a landing. Well, low altitude, yeah, it's landing. So they turned it off at 49 nautical miles. There was only a very narrow window where this alarm was on. It wasn't bad. A plane crashed, people died. But that configuration, those two lines in the configuration file were 1,000 lines apart. And a human evaluating it did not notice that conflict. Dr. Conte de Leon's research was how to analyze these config files to find these contradictions or these conflicts. That is now, you know, the developer didn't develop the tool to actually check for these things, so it's up to the administrator to do. And it was actually evaluated by the FAA and they didn't notice. So, you can have things like default router names and users user password list. So these were the router brands, default IP address on the router inside your house, default username, and default password. So a lot of these have changed now. I like that the new ones I bought, they have a sticker on it that says this is the default password. You know, it's no longer admin, it's something else. So how do we manage vulnerabilities? We need to design the system to avoid them. We need to write secure code to reduce the number of them. We need to add mitigation techniques to address them and analyze systems to find them. Software design principles, how we build more secure systems, that's what I want to talk about. We got to deal with common vulnerabilities and secure coding techniques for the right secure code, and then using code audit and code analysis tools, software testing. All right, so this is the part I wanted to get to, the first part. Salter and Schroeder's paper. So Salter and Schroeder in 1975, so that was a few months ago, came up with this list of good design principles for secure systems. There was an updated version in 2009. And then here, the IEEE Center for Secure Design talks about how to avoid the top 10 software security design flaws. And we'll cover all of this. Not today. Like I said, I just want to touch on Salter and Schroeder's. So there's were design principles. It's programming design principles, but it fits into networking design principles. It fits into operating system design principles. And there are three main underlying themes, excuse me. Getting wrong here. Simplicity. If your code is simple, if your system is simple, there's less that can go wrong. There will be fewer possible inconsistencies, and it'll be easy to understand. Restriction, minimize access, inhibit communication. Don't let your system wide open. This fits really well with operating systems and networks. Minimize access. If they're not allowed, if they shouldn't be in there, don't let them in. Inhibit communications. Why inhibit communication? If my system is compromised and it can easily communicate with your system, I could possibly compromise your system. And we've been doing a lot of work in that area for industrial control systems. If I have a device, a simple device, not very good, real-time operating system, not much security because it was assumed to be simple, and just reads measurements from a sensor and sends messages. If it gets compromised and has full access to the whole network, it can send messages to all machines on the network, eventually compromising from going from one machine to another, leapfrogging from one machine to another, compromising a more powerful machine, compromising a more powerful machine until it's fully in the system. And we also talk about the methodologies we want to do. Okay. So, least privilege. I just thought of something. Oh, I am. Okay. First principle is a principle of least privilege. And I think we talked about this several chapters ago. We talked about operation security, when we talk about human elements of security. Software or the user or another system should only be given those privileges that they need to complete their task, and only for the minimum time necessary. So we have a lab here that's an isolated lab for network attack defend type of things. Students who are taking a more advanced class can go into the lab to do things. Do they need access 24/7 to that lab? Years ago, we had some people, they just default, oh, we give you access to lab. So whenever you're in, you can just do a swipe card and you go into the lab. Well, they were able to spend some time in the lab copying all that malicious software that was on the lab onto a USB drive and taking it home to play with. Now, all the stuff we had obtained off the internet, so it was publicly available, but they shouldn't have been able to get in there and do that. That wasn't what they were authorized to do. Give them too much access. You want to have at least a minimal protection domain. Protection domain is all objects to which the process has access and the type of access the process has. So these are all the things that are readable. These are the things that are readable, writable. But I want to change it. I might want to say, if I'm running a web server, e-commerce server, right? This is things related to the customer's purchase. That's a different domain than stuff related to the catalog of what I can see. Rights will be added as needed and then discarded after use. It's okay to say you have permission for this limited time. And now you no longer have permission to do something because you don't need it. This fits into this need to know, need to access. Now here became, I'm trying to remember the term he used. Darn, I can't remember. Sorry, I was talking to somebody in the NSA years ago about this. And he said, so here's a scenario, designing a system, which you got to think about, military system. You have a gunnery sergeant in charge of a land-based gun. The guy has no security clearance. He's a grunt. He's very good at what he does. He needs to know where the targets are so he can shoot the right people. You got a spy plane going over the battlefield. It's running top secret, spy equipment and stuff. It analyzes the battlefield. It sees information. It sends that information off to the analyst. The analyst analyzed that information, combined with other information, and said, oh yeah, this convoy is shipping, weapons. We need these guns to fire at the convoy. There's a trick in getting that information, that top secret information that, hey, these are the bad guys you want to shoot, down to the guy who doesn't have a security clearance. But he has a need to know at that time that information. So there was a lot of discussion about how to do that. The other example he gave was like a pilot. He says, oh, pilot's flying a sortie over there. They find a target of opportunity, up pops out on his window. You have targets. Need to know at that time. And I'm trying to remember, he had a different term for it.
You're talking about a Brago?
Hmm?
Brago, it's like a message when you're to go in a target.
Yeah, so, but it was a different term he was using, but. So these are things we have to think about: least privilege, who needs stuff when. Okay, the advantage of least privilege, it reduces the risk of a breach. If I don't have access to some data and somebody breaks in and gets access to my account, they still don't have access to that data. So the security impact of the incident or corruption of the component will be minimized. A security analysis of the component will be simplified. That is, if I have to do a forensic analysis on a breach, the analysis will be easier. I know, oh, they breached this component, this piece of software, this user's account. I know what they had access to. I don't have to check the whole system. And we protect confidentiality. People only get to see what they should get to see. Fail-safe defaults, and this fits into firewalls and operating systems, unless a subject, which is a user or a piece of software, whatever, computer, is given explicit access to an object, so the subject's what you're doing the action, the object's what's you're operating on, so a file, a device, a piece of software, whatever. Unless it's given explicit access to the object, it should be denied access. I'm not given explicit access to your homework. I should not be able to see your homework or modify your homework, especially if it's not for this class. If an action fails, the system will still be as secure as when the action began. That's what we want by fail-safe defaults. Assume the answer is no. If you ever have kids, fail-safe defaults say no first. Of course, they'll find a way around that. They'll ask you a double negative or something, just. And I had a supervisor too, who was, if you ever asked for money, his default answer was no. And you always had to ask a second time with more details. Okay. But the first firewalls that were invented, the default was yes. It was a blacklisting. These are the people who will deny, let everybody else in. Finally, it's like, no, we're gonna not let anybody in except doing these things, the whitelist. So what happens when a system fails? Some system allows access or exhibit insecure behavior when a failure occurs. I should say some systems. That's not good. If a failure occurs, the default should be, the fail-safe default should be nothing happens, nothing bad happens. Otherwise, the attacker can just figure out how to cause a failure and cause your system to shut down and cause whatever happens bad to happen. If I'm unable to complete any action or task, all interim changes should be undone. Security state restored prior to termination. So think about this. Going to a bank, attacking a bank account. I get part way, I get it to take money out of your account, start transferring my account, the system figures out something went wrong. The default should be your money goes back into your account. Grain elevator, we're dumping grain into the back of a delivery truck. Grain's being dumped. Failure occurs, we shut it off so no extra grain goes into the delivery truck. But there's no way to go back to the beginning state where all the grain's back in the elevator. It's still in the truck. There's some things you can't revert. With software and with electronic data, often you can revert back to a known good state. Physical systems, you can't always do that. So you have to then plan for what to do if this failed. Economy of mechanism. Keep software design as small and simple as possible. We hate spaghetti code. code that just hops all over and does a whole bunch of weird things. Keep it simple and small. Don't add complexity that's not needed. Simpler means less can go wrong. Simpler means it's easier to see what's happening, to understand as a human being what's happening, or for a tool to understand what's happening and see if there's a problem. And when errors occur, they're easier to understand, but easier to fix. Complete mediation. Software should validate every access to every object to ensure the access is allowed. You know, my access starts as false. I check the access. If it's now true, I can access the object. Here again, I check the access. If my access is true, I access the object. I checked it here, I checked it here. If I didn't do this check and something changed in between these two, where suddenly I was no longer allowed access, but because the code said, assumed I did, it gave me in, allowed me in. So if there's a privilege change, and for sometimes that is, especially on network systems, we need to make sure we keep checking. Every request, it's time consuming. Usually we say, put a small piece of code that checks each time. A lot of people won't do this. Separation of privilege. Our defense in depth. Software should not grant access to a resource or take a security relevant action based on a single condition. Sensitive operations should require the cooperation of more than one check. Banking, like 2 signatures on a large check. Military, 2 people to give the same command. Verification, validation of things. But dual factor login. Things like that. Okay, transferring money, maybe it's reimbursement for a trip. I submit the paperwork, somebody checks all the paperwork, checks all the receipts, says yes, I approve it, it's authorized to go to this account, then a second person looks it over. And then it actually at the university, then it goes to a third person who actually cuts the check. Okay, and when they cut the check, somebody else checks that they're cutting the check tied into an authorized reimbursement. So lots of checks and balances because the university has a lot of money going around, floating around. Open designs. Thinking no one's going to find your key when you put it under the doormat. Thinking no one's going to figure out the vulnerability or the backdoor into your system because you didn't tell them. I think of the old War Games movie. The designer, there was a default user account, his son's name Joshua, I believe it was. Gets you into the system without having to have a password. He put that backdoor in so it is easier for him to go and check the system. Designers do this all the time. They have ways to get into the system that are non-standard. They bypass the security because, hey, only they know about it. I was working years ago with a company developing a crypto system. And they bragged about how secure it was until I saw the design. And then I realized there was a major flaw in design, and I wrote a piece of program that cracked it in a minute. So it was really a bad design flaw. But nobody else had seen the design flaw because they were trying to keep it secret. Assume the developer of your code took your code, all the design documents, and themselves and went to work for the adversary. Is your system still secure? Security should not depend solely on secrecy of the design or implementation. Now, this doesn't apply to passwords or cryptographic keys. Those we understand. Those are all about security. You keep those secrets and you're secure. But the whole algorithm it's implemented, the whole DES algorithm is out there. The whole AES algorithm is out there. RSA is out there. We know how they work. I can give you my public key, part of my public key, and I'm still secure. That's what we want. So security of the software and of what the software provides should not depend on security of the design. Least common mechanism. This is a tricky one for a lot of people to understand. Mechanisms used to access resources should not be shared. Now, we have a lot of shared libraries, a lot of shared code, shared cryptographic algorithm. That's not what this means. What it means is, so on campus here, we have the library and you can check out books. We have a biosafety lab where people do experiments with biosafety stuff. We have our secure computing lab. Does everybody go through the same person to get permission to access those facilities? The same person makes the same decisions for everybody. That's a least common mechanism. If all of our requests are going through the same source and all of our resources, all of our information are shared and available within that source, that's a common mechanism. So I'm not talking about, hey, you wrote this crypto code and I'm running it, you're running it, they're running it. That's okay. If it's, we're all using the same encryption keys, same passwords, that's not good. So we want to share as little as possible so that if we shut down one thing, we don't shut down at all. You know, we break one thing, we don't break it all. I like this one, least astonishment. Security mechanisms should be designed so users understand why the mechanism works and roughly how it works. And that using the mechanism is simple. Hide the complexity introduced by the mechanism. Make it easy to install, easy to configure, easy to use. And this is where I have seen so many problems out there. Human factors is critical. How does the human interact with the system? If you say they will get used to it, you have failed. Did I mention the remote control example of my wife? So she took a human factors design class here. And she was a human factors psychology major, but this was a human factors in mechanical engineering. The instructor required everybody to develop in teams a universal remote control for TV, whatever. And so each of and he said there were some requirements on it. And one was that it needed to be usable by men whose hand sizes were up to the 95th percentile and women whose hand sizes were down to the 5th percentile. My wife's 6th percentile, so she has a small hand. He then took these mocked up designs and handed them out to students to try and make sure my wife tried every single one of them. And one of them my wife puts in her hand and holding her hand with her thumb, she could not control both the changing the channel and the volume. She had to use her other hand to do that. She says, I don't like this. But like, why? She says, I can't do both. I want to change the volume and the channel with one hand. Everybody wants, you want to use that remote with one hand, right? And they said, oh, she'll get used to it. They actually said that in class in front of the instructor. Oh boy. Just, you know, engineers, oh, I'm used to this. I know what this means. I see error messages. You know, the first one, SYN error, when I was programming in BASIC. It was a syntax error, but they abbreviated everything because there's no memory on the systems. I had no idea what a SYN error was. You get error messages when you're coding it that may not say anything. You know, segmentation fault, but you don't even know what line number it occurred on. Okay. Configuring systems. Oh, I want to do remote logging of using public key certificates, and I have to do steps A, B, C, D, and E for it to work. And people always forget step D, which is verify the signature. Well, not always, but a lot of people forget to verify the signature of the certificate that you retrieved. They just use it. Give me your digital certificate. Okay, here it is. Thank you, I'll use it. Instead of checking that actually it was a valid one, you didn't fake it. Because the complexity, the steps, and we've seen this in a lot of cryptographic systems, a lot of cryptographic libraries, a lot of security tools. The steps are complex for the developers who haven't been trained on it to actually use. The last example related to this, maybe it'll tie. I don't know if any of you assembled something like a furniture or a toy. I remember putting together bicycles and tricycles and other stuff for my kids. You're going through, okay, you know, put, you know, bar A in slot B, tighten with screw C. Turn the page. But first. No, don't say but first. That happened to me on a couple of things, and then, you know, where it's like, okay, now I got to go back and see if I can undo what I did because it said, but first, don't do this. Don't over tighten. Oh, I did. Keep it simple, least astonishment. It should make sense to the users. This will not always happen. There are people who just don't think the way you do. There are people who don't think the way computers do. Something may be obvious to me, but it's not obvious to you. I may not understand why it's not obvious to you. And so our communication gets to be a problem. Right, so you think about that. And I run into examples of this all the time where I say a word or somebody hears a word and they think one thing and I think something completely different. When I say the word goal, what do you think of? Football. Achievements. Two good examples. Soccer, hockey. Oh, I thought you meant precious metal. I thought you said gold. I misheard you.
Seagull.
Seagull. Hey, there you go. Spelled different. These are things just, so we want to keep it simple. One, understand that not everybody is trained the way you are. Not everybody has the background you do. I know I have a hard time with this. I've been programming since before. Well, I wrote my first line of code in 1978. It's most of you weren't around then. So I have a lot of experience. I've done this a lot longer than you. And I forget there's things that are intuitive to me that I assume people understand. My kids play a lot of role-playing games like Dungeons and Dragons and stuff. And they're shocked when people have a hard time understanding the concept of percentages. You have a 10% chance to hit. What does that really mean? Or 1 out of 5. One of my favorite t-shirts is 5 out of 4 people don't understand fractions. And some people are like, what? So just think about this with the least astonishment principle. Human factors matters. Okay, I'm gonna stop there. I'm not gonna go on the rest of this because that should be enough for this. I went a little faster than I expected. But again, thinking about network design, operating system design, those things, you can keep some of these principles in mind. Separation of privilege, least astonishment, least common mechanisms. Questions? All right, I will stop there. Exam in class Thursday. I think we'll have our highest attendance again in a while.